Okay, now for what we have in this problem set, we have in the crossover to first order linear differential equations, and we have for the general layout, okay, we have the derivative dy over dx, and the variables do not have to be limited to just x and y, but in the setup we have y as the dependent variable, x is the independent, and here we have dy over dx plus p of x times y is equal to q of x. And first order linear differential equations can be solved through the use of an integrating factor, which we have involving the natural logarithmic base e, which is raised to the integral of p of x dx. And for what we have in the case of number 9, we have xy prime minus y is equal to x, and we have an initial condition whereupon we have y of 1 is equal to 7. And if I put this with the leading term as just y prime, so I can go ahead and divide this equation by x, whereupon we're just going to rewrite in terms of the standard first order linear differential equation display. Okay, so if I divide the equation by x, and so okay, in the rewrite, okay, you have y prime. I'll just go ahead and use Leibniz's notation. Okay, so you have dy over dx, and we have minus, you could say y over x, but just to stress what p of x is, okay, that is going to be the negative of 1 over x, and dividing x by x, okay, I have is equal to 1. So we have for the setup, so we have that p of x equals the negative of 1 over x. And for what we have in the case of the integrating factor, so we have e to the integral of negative 1 over x dx. And that's going to be equal to e to the negative of the natural logarithm of x. And once again, translating the negative coefficient to a power of negative 1. So we have e to the natural logarithm of x to the negative 1. So the integrating factor, we can say is going to be x to the negative 1, or the reciprocal of x. And multiplying the standard layout by 1 over x. So we have 1 over x dy over dx, and we'll have minus 1 over x times 1 over x, so we have minus 1 over x to the second, and we have is equal to 1 times 1 over x, so we have 1 over x. And we have in the rewrite, okay, the left-hand side of the equation is going to turn out to be the expansion of taking the derivative in x of the product of the integrating factor times the dependent variable y. And looking at freeing up 1 over x times y, I can integrate over both sides. Okay, so I got 1 over x times y, so it'll be y over x, and we have is equal to the integral, so just going from the derivative in x, okay, to integrating over x on both sides. And looking at what we have now, okay, so you have y over x is equal to the natural logarithm of x followed by the constant, and multiplying by x, so you have y is equal to x times the natural logarithm of x c times x. And looking at the initial condition, going from the determination of the general solution to the complete solution. Okay, so we have y of 1 is equal to 7. And substituting. Again, so you have y is equal to 7 whenever x is at 1. And the natural logarithm of 1 is going to end up at 0. And c times 1 is c, and we have it's equal to 7, so we have right away that the missing constant value is going to end up at 7. So we're going to have that y is equal to x times the natural logarithm of x plus 7x. And you can also write this in factored form. We have x times the quantity of the natural logarithm of x plus 7. Okay, for what we have in the case of number 10, we have a first order linear differential equation, and we don't have this presented in standard form yet. So taking care of the coefficient alongside the first order derivative, where we have change in y with respect to the change in x. Okay, we got 2x that we can just move or take care of upon dividing. Okay, so we have in the rewrite, so I'm just going to once again rewrite y prime in terms of Leibniz's notation. Okay, so we have dy over dx minus 3 over 2x times y, and that's just to stress the value or what we have for p. And 9x cubed over 2x, okay, so that is going to be 9 halves of x squared. Once again, we have with p, we have minus 3 over 2x. And that's going to be negative 3 halves of the reciprocal of x. I'm just doing this in advance so as to make the integration and the determination of the integrating factor a little bit quicker. So we have for the integral p of x dx, to which the natural logarithmic base e will be raised. So we can say we have e to the negative 3 halves of the integral of 1 over x dx is equal to e to the negative 3 halves of the natural logarithm of x. And again, rewriting the coefficient as an exponent. So you have e to the natural logarithm of x to the negative 3 halves. And so we can say we have x to the negative 3 halves or rewrite this as the reciprocal of x to the 3 halves. And so taking the product of the equation and the integrating factor, I mean the product of the standard form layout. So you have 1 over x to the 3 halves. Again, we have dy over dx. Minus, again, we see we have minus 3 over 2x, and x to the first times x to the 3 halves. Okay, so that's going to be x to the 5 halves. We have times y. And we have is equal to 9 halves. And x squared divided by x to the 3 halves, that's going to be x to the 1 half. And again, if you don't care to do all the multiplication on the left-hand side, just note that the end that has the derivative, those two terms will form the expansion in the derivative with respect to the independent variable of taking the product of the integrating factor times the dependent variable. So looking at what we have in the setup, so we have d over dx of y over 3, or I should say y over x to the 3 halves is equal to 9 halves of x to the 1 half. And undoing the derivative, and we have integrating with respect to x on both sides. Integrating on the left hand side just undoes the derivative, and we have is equal to 9 halves of the integral of x to the 1 half dx. And we have for the antiderivative, again this will be 2/3 of x to the 3 halves. And for what we have in the follow through, so we have 9 halves of 2/3, so that will be 9/3 or 3 times x to the 3 halves, followed by the constant, and multiplying by x to the 3 halves, we have that y is equal to 3x cubed plus c times x to the 3 halves. Okay, for what we have in this problem, okay, now we have a first order linear differential equation that is not yet on display in standard form. Now we have the derivative term so far, xy prime or x dy over dx is set equal to 2y plus x cubed cosine of x. So I can do here to get the derivative and the first order y terms together. Okay, so if I take 2y away from both sides, so I have xy prime minus 2y is equal to x cubed times the cosine of x. And to get the derivative term in terms of just dy over dx or just plain y prime, so again I can just divide the equation by x, and so we'll have in the rewrite, we can say again y prime or dy over dx, and we have minus 2 over x times y, and we have is equal to x squared times the cosine of x. And we have for the y term, after converting the equation to its first order linear standard form, so about p of x is equal to negative 2 over x. And for the integrating factor, so we have e to the integral of negative 2 over x dx that is equal to e to the negative 2 times the natural logarithm of x, and that is e to the natural logarithm of x to the negative 2. And we say we have x to the negative 2 or the reciprocal of x squared. And again, if you multiply the equation by the integrating factor, and what I'll do here, okay, just to sort of give you a shortcut, and we have x squared divided by itself, so this will end up as the cosine of x. And again, for what we have on the left, okay, now you could distribute without doing any of the excess in terms of working with the exponents and the product property. Okay, now what you're going to have here is at the left-hand side, after you multiply by the integrating factor, again, those terms will be the product rule expansion of taking the multiplication of the integrating factor times the dependent variable again, which will be y. Again, on the right we have the x squares to cancel, so we have the cosine of x. And for what we have, once again, integrating on both sides of the equation. So to the left, okay, we have y over x squared is equal to the integral of the cosine of x dx. And so we have y over x squared is equal to the sine of x followed by the constant, and isolating y, okay, once we multiply by x squared, you say that we have x squared times the sine of x plus cx squared, and again you could have left that in factored form as x squared times the quantity of the sine of x plus c. Okay, for what we have in 22, we've got another first order linear differential equation, and this one is not quite on display in standard form. Okay, now we do have the dy over dx without any coefficient besides 1 alongside it, but we want the derivative term and the first order y term to be on the same side. Okay, so I will deduct 2xy from both ends. So we have dy over dx minus 2xy is equal to 3x squared times e to the x squared. So we have for p of x that is equal to negative 2x, and for the integrating factor, so again we're going to have e to the negative 2x dx, and that's going to be equal to e to the negative x squared. And if I multiply the equation by e to the negative x squared, again I'm just going to use a little bit of a shortcut. Not really a shortcut, but just save the trouble of having to write out exponents quite so much, especially on the left-hand side. Again, I could have distributed e to the negative x squared over the left-hand side, but for what we're going to have, again, those terms would end up being simply the product rule expansion, taking the derivative nx of, once again, the product of e to the negative x squared times the dependent variable. And for what we have to the right, okay, you have 3x squared, and for e to the x squared times e to the negative x squared, the result will be e to the x squared minus x squared, and that would be e to the 0, which is 1, and 3x squared times 1 is 3x squared. And integrating over both sides, so we have e to the negative x squared times y is equal to the integral of 3x squared dx so we have e to the negative x squared y is equal to x cubed plus c. Now for the general solution, okay, we have y is equal to x cubed, and if I divide by e to the negative x squared, this will be the same as multiplying by e to the positive x squared. And again, we had an initial condition whereupon y naught is equal to 5. So in this case, right, so you have 5. X cubed is 0 to the third. Okay, so that is negligible. And we have 5 is equal to c times e to the 0. E to the 0 is 1. So we're going to have the value of the constant will be at 5. And with the value of the constant determined, we can now say that y is equal to x cubed times e to the x squared plus 5 times e to the x squared we can also factor out as e to the x squared times the quantity of x cubed plus 5.